In the 16th century, Galileo gave an example about the classical idea of relativity. He's saying that assuming that you are sitting in the ship and this ship is going with a constant velocity, and assume that the ups and downs and all this shaking of the sea is not that much that we can understand the direction of the movement from it. Now assume the water is falling from the ceiling of that room in the ship. Can we understand the direction of the movement of the ship based on the trajectory of water falling down? Why do I ask that? Because the primary idea was that the water is releasing from the ship and it is not connected to the ship anymore, and if the ship is moving, the water is somehow falling behind. And we see it move into the opposite direction of the ship movement. Please pay attention that we are talking about constant speed, not constant acceleration. If we do the experiment, we see water comes down into a straight line. What's the reason? The reason is that the water which is coming down also has a speed equal to the speed of sheep and equal to the speed of us. This is classical relativity. A modern example of it is driving in the highway. When you are driving in a highway, even if you have a very high speed, you see the cars around you are stationary or even they have a very slow speed. Why? Because the relative speed is zero. Pay attention. The speed is relative. One of those concepts that took a long time for human being to realize that was that the speed of light is very, very large, but not infinite. This speed is so large compared to ordinary speeds around us, and we can never imagine moving with that speed. How would it look like? It is so large that in 1 second we can go around the earth for 7 times. So we don't see anything simultaneously. We are always looking at past. And this cannot be understood in ordinary life. By seeing, I mean a camera which is recording the exact location and a time of an event. That is the meaning of seeing in terms of experimental or measurable seeing. Ole Romer was the first one who indirectly measured the speed of light. He calculated the ratio of the Earth's speed to the speed of light. He realized one of the moons of the Jupiter seems to have a different periods in different seasons of the Earth. Which means in summer or winter or fall, there are different periods are recorded for the Io. The reason that he exactly picked Io was probably a good observational angle from the Earth. He correctly assumed that in the different seasons of the Earth, for example summer and fall and winter, Earth has a different motion relative to the Jupiter. Sometimes the Earth approaches the Jupiter and sometimes the Earth goes further than Jupiter. When the Earth is approaching Jupiter, this period is less than the normal period, and when the Earth is going further from Jupiter, the period increases. You can see the mathematics of this calculation. It's not very complicated, just a little bit of cinematic. But he could measure the ratio of the Earth's speed in the orbit around the Sun to the speed of light. This number was around 10,000. He didn't calculate the speed of light because he didn't have the speed of the Earth, but later on, another astronomer and mathematician named Christian Huygens calculated this speed. With 20% of the error, this number was very accurate compared to today's number. He also discovered one of the moons of the Saturn named Titan. The first direct measurement of the speed of light was done by James Bradley, an English astronomer. He used light aberration as the way to measure the speed of light. Light aberration means the angle that we are receiving the light from further star depends on our relative speed compared to those stars. A daily example of it is raining. So when we are stationary under rain, we receive the rain with zero angle. But if we start to run, we feel it on our face with a different angle. So if we consider a certain group of stars that we know the relative motion of us compared to them in different seasons, we can think of them as the reference star and calculate the displacement of them because of the different angle of light receiving by us. So this star seems to be a little bit of offset upper or downer or left or righter than the real place. So by measuring this displacement, we can directly calculate the speed of light. In 19th century, an English physicist, James Clerk Maxwell, proposed 4 equations to explain how electric and magnetic fields are responsive to electric charges and the current. These equations are basically connecting the derivative of a field and the changes to the charge density and the current. But an interesting thing about Maxwell equation is that it can predict the exact speed of light based on 2 constants of the nature. This was remarkable. Imagine predicting the speed of light just as a function of completely independent variables. This was a huge success, but there was something strange about it. It was that this speed does not depend on the frame of reference. You remembered we talked about relative speed. It looks like that we cannot have any speed relative to light. And it was in contradiction of mechanics. In the last video, we talked about the paradoxes of the orbital motion of the electron inside of the atom. This was another paradox. In mechanics, if you move relative to the medium that the wave is moving on it, you see the wave to be stationary. But looks like that it was not the case for electromagnetism. Which one is telling the truth, electromagnetism or mechanics? There is a little bit of illustration here. This is the imagination of mechanics. On left side you see the frame of reference, and on the right side you see the detector of light. As you increase the speed to the speed of light, you might see the light to be completely stationary and the frequency of light goes away. And this one is the prediction of electromagnetism. No matter how fast you move, you can never see the light stationary. One of the questions in classical mechanics was that at the end, who is stationary? Which frame of reference is sitting there? Earth is moving, and Sun is moving, and the Milky Way is moving, but all of them are moving in respect to what? That was a long time imagination that we're thinking that something called ether, or the ocean of light, is surrounding everything and it's big enough to cover all the galaxies and stars, so the light can reach us. And we are basically moving relative to ether. Well, if there is an ether, how can we measure the speed of Earth in the ether? 2 American physicists named Albert Michelson and Edward Morley for the first time decided to measure the speed of Earth in the ether. What was the idea? They were thinking that if we are sending a light ray parallel to the Earth motion, and if we are sending a light ray perpendicular to the motion of the Earth, we see the difference in the velocity, and as a result we see the path difference between the 2 light rays. The one which is parallel gaining more speed, and the one which is perpendicular is just having the regular speed of light. So if we bring them together in a point, we should see some interference pattern. If one of them is falling behind somehow from the other one, the interference patterns show destructive interference, which means the 2 light rays are not just summing up, but they kind of cancel each other. You can see it in this illustration that at certain phase shift, this is completely destructive. They did the experiment and they basically saw nothing. No destructive interference pattern, which means the speed of light is always the same, parallel or perpendicular. Electromagnetism 1. Some people try to explain why this is happening. Like Henrik Lorentz, a Dutch physicist who tried to explain it based on Lorentz contraction, or Henri Poincaré, French mathematician, based on the idea of invariances under certain transformation. But neither of them were brave enough to say, hey, the relative value is not the speed, it's time. And this is where Albert Einstein comes into the story. Let's talk about time a little bit. We measure time based on the periodic motion of a pendulum or a spring going back and forth, giving us an idea of time. This is what we are calling it a mechanical clock. So if we are looking at a mechanical clock, we realize that the period of the mechanical clock is a function of mass and the constant of the spring, and it is not affected by the motion. Basically saying all the clocks, no matter in the train or outside of the train, working with the same pace, or basically the rate of the tick-tock. If you change the spring or the mass, change the mass, you realize the period change, but this period is not affected by motion or velocity. So in classical mechanics, the time is universal. Now let's go to the story of Einstein. At that time, he was an examiner in a patent office in Bern. In 1904 and 1905, he published 4 papers that are so important in the history of physics, basically revolutionizing all the things. One about photon and the quanta of light, one about Brownian motion, one about the electrodynamic of moving bodies, which is relativity, and the other one is about mass and energy equivalence. Well, Einstein saw something that the other people didn't see it back before in time. He noticed that there are some paradoxes about ordinary time that we just talked about. He asked, how do we synchronize a clock systematically? Well, first configure those clocks, put them on the grid. Now go back to the origin, send the light ray, and let it one by one hit the clock so they all turn on in a way that they are all synchronized. Well, there is nothing wrong with that. That's correct. But you know what was the problem? The problem was that when 2 people are starting to synchronize their clock and one of them starts to move, and if they both use light, which has the same speed in all of the frame of reference, each of them see the other clock is falling behind from their own clock at the moment of synchronization. The light is going with the same speed for both of them, but one of them is going far and the light takes time to reach that clock. So that clock is falling behind the other one. So he said, 2 observers cannot agree on the synchronization mechanisms, each accusing the other one not to have a synchronized clock. But both of them are telling the correct because this is what they see. Einstein also criticized the mechanical clock and he said, no, we should make a universal light clock, which is based on the periodic motion of light ray up and down. How to make this clock? Easy. Put 2 reflective mirror and then put a light ray that goes back and forth, and this is your basically tick-tock. Tick-tock. It is up to you the separation of the 2 mirrors that gives you a different rate for your tick-tock. But if you make such a clock, something very interesting is going to happen. If somebody is looking at his own clock and looking at the other one, which has a constant speed compared to him, he sees the light ray getting some horizontal speed. Again, the speed of light is constant. So for keeping the speed of light constant, the light has to lose some of its vertical speed. And if this speed goes up more and more, someone who is standing outside of the train is seeing that clock is working slower than his own clock. You can actually work out the mathematics of the relationship between the delta t and delta t prime. This phenomenon called time dilation, which means if you're outside of the train and looking at the train, you think the train clock is working slower than your clock because of simple geometry. Again, this stands on the assumption that the speed of light is the same in all frame of reference, the consequence of that. At the end, let's review how Einstein solved this issue. First, he took a side of electromagnetism, saying the speed of light is constant and it is universal. It is not one of those velocities that you can define it relative to something. Next one is about time. He pointed out that time is not universal. Time is defined based on the relative speed of 2 frame of reference. If I'm standing here and looking at somebody's light clock, which is moving relative to me, I see their time is working slower than my time. And the last one is about the frame of reference or ether. in classical mechanics, everything should be compared to those ultimate frame of reference, which is stationary. We call it inertial frame of reference, which means the laws of physics are held inside of that frame. But Einstein came and he said no need for that frame of reference. All the frame of reference are equivalent, and the way that we can understand something is inertial is that it is non-accelerating or somehow flat, which means any frame of reference that doesn't have acceleration is the same as the other one.